Zoom has changed. Well, anyway. Okay, there we go. Okay, so good. So this course is about computability theory. More or less what this is it is the theory behind what is and what is not computable by an algorithmic process. So an algorithmic process is an algorithm that you or I could carry out by following the steps, but quite often that would be very tedious and take a very long period of time. So nowadays that a computer could carry out by following the steps. But as probably you're all aware, although computers are amazingly powerful, there are limits to the power of a computer. So they're not unlimited in power. And computability theory is largely about understanding the boundaries between what is computable and what is not computable. Okay, so I realized I forgot to need to remember which buttons are which for the camera. So sorry, you can't see what's happening on the screen, but the settings have been incorrectly set up. So, but honestly, these will be hopefully teething problems and not going to repeat all the time. Right. Okay. So what is and what is not? What is not computable following an algorithm? So by an algorithm. So the way this arose historically is, so in mathematics, algorithms have been very important going right back as far as you can possibly go in mathematical history. So the algorithms were important to the ancient Greeks. So for example, one of the most famous early algorithms is even in Euclid, which is Euclid's algorithm for computing the greatest common divisor of two numbers. So many famous algorithms here in mathematics. that's a beautiful algorithm, something we all learn early on in our mathematical careers. Euclid's algorithm for computing the greatest common divisor. Even before that, we learn some important algorithms at primary school. So you learn how to, when you're learning maths at primary school, you learn how to add numbers, writing numbers on top of each other and going down the columns and adding them and carrying and so on, and to multiply numbers using what in English is called long multiplication, and to divide numbers using long division. And all these processes are essentially algorithms that you're following. Of course, they're taught to children as just a sequence of steps to follow, and it's easy for children to make mistakes, even adults, although you never really need them in practice because we have calculators. It's easy to make mistakes in following them, but nonetheless, there's an algorithmic process there. So these are obviously important algorithms, but so algorithms to add, multiply, subtract if you want, but anyway, subtract, I've said it, to write it down, multiply, divide, numbers, given in the ordinary notation we use, like base 10 notation. If we want to compute numbers, then another set of algorithms that's used in mathematics are the algorithms used in calculators for computing more complicated kinds of expression than just simply sums and products and divisions between integers, between whole numbers. So behind those kinds of algorithms for computing, say, real numbered values of more complicated mathematical expressions, there are essentially algorithms to approximate to any degree of accuracy the real numbers. So such as calculating pi, it's a benchmark for high performance computing. It's one of the challenges that people do in order to show they've got a very good high performance computer is calculating pi to a record number of decimal places within a reasonable amount of time. So similarly, you can calculate decimal places of e, or the result, say, trigonometric, exponential, or exponential functions, or any other kind of, all the kind of functions that appear in ordinary mathematical expressions. So let me just put etc for etc there, because obviously lots of different algorithms, lots of different such mathematical expressions one wants to compute. Roots are another, roots and powers of real numbers are another thing that's very important to compute. And then there are, so these two, historically very long standing, the first two. People were interested in, say, calculating digits in pi and calculating the results of trigonometric functions and logarithms and so on to produce tables of logarithms and tables of trigonometric functions. And I mean, these are things that have been around, that were around and important in the 19th century. So people have been interested in this since the 19th century. Now, of course, all this is done by computer. But in the modern age, since digital computers were developed in the post-war period after the Second World War, lots of other high-power algorithms have been developed for all sorts of specific purposes. So then there are more modern algorithms that are carried out on computers, and there's of course an endless list of such algorithms, essentially. So one doesn't really want to single out any particular algorithms here, but important algorithms would include things like the simplex algorithm for linear programming, or I think another one I put in the notes is a very important algorithm in cryptography, is an algorithm to test a very large number and see whether it is very probably a prime number. So this is how cryptographic keys are chosen by applying an algorithm like this to find large prime numbers, and then using the large prime numbers to generate, in a certain way, cryptographic keys. Anyway, there are many more modern algorithms. But the point is, algorithms have a very long history in mathematics, and for a long period of time, right up until the 20th century, the start of the 20th century, so 120 years ago, mathematicians were just happy to deal with algorithms by, the important thing was to have an algorithm to deal with the problem you have at hand. So, for example, if you want to compute digits of pi, which some people are very interested in, we have nice algorithms for computing digits of pi. They were very tedious to carry out before computers, but still people were applying these algorithms, spending years of their lives going through the steps, following the steps, and sometimes making mistakes. There's a famous story about somebody that calculated pi to something like 700 and something digits, but actually made a mistake at about the 300th digit. I don't remember the numbers. This was in the 19th century. And so more than half of the calculation was wrong. And this was his life's work. So, he didn't live to find out that it was wrong. that was discovered after his death. Anyway, mathematicians were just content to know what an algorithm is to be able to apply an algorithm when they want to compute something. It's around the turn of the 20th century, the situation changed for a reason that mathematicians became interested in finding algorithms to solve certain problems, and no matter how hard they tried, they were unable to find algorithms to solve these problems. So a very famous such problem was raised by David Hilbert, or David, I guess. No, he's German, so David Hilbert, in his famous address to the International Congress of Mathematicians in 1900, so at the start of the 20th century, when he posed a certain number of challenge problems that shaped mathematics for the 20th century. So solve these problems, and it was a big, very big thing in mathematics if you managed to solve one of Hilbert's problems. And among these problems, and I've got wrong control here, so among these problems was Hilbert's 10th problem. I'm going to write on the board now. So Hilbert's 10th problem was find an algorithm that will test or decide, we say, is the technical word, this means either answer yes or no to a certain question, that will decide whether a given Diophantine equation, that's the English pronunciation of it, has a solution. So a Diophantine equation is an equation between polynomials in which all the coefficients are integers. Maybe I should specify that we're trying to find an integer solution. So this subsumes many questions like, well, it doesn't quite subsume the questions, but I mean, one can formulate any instance of Fermat's last theorem as a Diophantine equation that won't have a solution by Fermat's last theorem. But it's not completely trivial to do that because here I'm talking about integers and you have to rule out the case zero in some way. Anyway, I don't want to get sidetracked by that, but in any case, the idea is you give the algorithm the coefficients of a multivariable polynomial, that integer coefficients, and you want the algorithm to do a bit of computing and come up with the answer yes or no. Yes, it has a solution. No, it doesn't have a solution. Anyway, so this was a good challenge for mathematicians to think about, and they thought about it, and for a long time they thought about it, and they didn't find an algorithm. And that's how things stood. In the meantime, I mean, I've forgotten how many questions Hilbert posed in his 1900 lecture on mathematics. I should have looked into that before this lecture. But he posed a lot of questions, but he wasn't done with questions in his list of questions at the 1900 in International Congress of Mathematics. So in the 1920s, and let me look at my notes to remember, I think it's 1928. So Hilbert's 10th problem was from 1900. And in 1928, Hilbert came up with another problem about finding an algorithm. But in the intervening 28 years, a lot of very good work had been done on the development of the subject that's called mathematical logic. And Hilbert's problem in 1928 specifically concerned the field of mathematical logic. So actually, it's less easy to understand than the first problem about Diophantine equations, because it's harder to say what the words mean, and I won't do that. I'll just state what the problem was. So he called this his Entscheidungsproblem, and I believe I have that written correctly in the LaTeX notes. I don't want to embarrass myself by writing it out incorrectly on the board. So, Entscheidungsproblem. I don't even know if the T's there. Let's call it his E problem. This was from 1928. And this was another. Here's something else I can't find an algorithm for. This was so challenge to mathematicians, find an algorithm that will decide whether a sentence in first order logic, this is a statement written in formal symbols that expresses a mathematical property. But the word sentence has a formal meaning here. So a sentence in first order logic expresses a property that is true in all possible mathematical structures. In other words, that is logically valid. So you need to know a bit about logic to know what this means, and that's not necessary. It's not possible to provide that background in this lecture. So we'll just accept this as a good question. It was a very good question. So it is logically valid, i.e., so let's explain that a little bit, but again in terms of words that only have meaning if you know something about logic, i.e. true in all mathematical structures. So here the idea is, give me a sentence that expresses a property. Is that property necessarily true? True in all structures. Okay, it was a very good question. It was very natural in the context of the mathematical logic that had been developed during the first 3 decades of the 20th century. And this is the question that first got an answer, the second one. So the reason I'm mentioning this, even though we don't all have the knowledge to understand exactly what it says, is because this is the important question that in the end started off the field of computability theory. Because this problem got quite quickly solved. And the solution was discovered independently I mean, it's not actually going to be a solution to the question as posed exactly there. So let's say the problem, the second problem, the E problem, was solved by Alonzo Church and Alan Turing. You will have certainly heard, I guess most of you have heard of Alan Turing, a very famous British person from the 20th century that had an interesting life story, and lots to discuss about Alan Turing, but he's become more and more appreciated in culture more recently, and he's become so appreciated that when the Bank of England, about 2 or 3 years ago, came up and printed new banknotes, so Alan Turing is the person that they put on the new £50, so just for the last 2 or 3 years, new £50 note in Britain. I don't actually know what's going to happen to these notes now that the Queen has died, because if you've ever been to Britain or you've seen British money has the Queen's head on everything, so all money is going to change now. I have King Charles's head on, and maybe the other people that were on the notes are going to change. But anyway, Alan Turing has enjoyed a few years in the limelight as the head, the non-regal head on British money. But why do I say solved here in inverted commas rather than actually solved? And the reason is that their answer was not to find an algorithm. The answer was, it is impossible to find an algorithm to solve this problem. So the answer is there does not exist an algorithm. So there is no point trying to look. There does not exist such an algorithm. It's impossible to find one. They turned the question around, but in doing so, they were able to come up with an answer. So, in technical terms, one says that the Entscheidungsproblem, there's no algorithm to decide it, so it is undecidable. There is no possible way of deciding it. So, technically, the Entscheidungsproblem, the E problem, is undecidable. So Church and Turing did this independently, but in the same year, in 1936. I think Alan Turing was an undergraduate at Cambridge University in England, and there was a lecturer there that gave some lectures on logic and lectured Alan Turing and said, Hilbert has asked this interesting problem. And Turing went away and came back 2 weeks later and said, oh yeah, I solved that problem. And then wrote it up in a paper that we will talk about in the next part of the lecture. But just to complete the story here, the Hilbert's tenth problem was also solved, building on the ideas of Church and Turing, but it took quite a lot of time to get there. So it was solved in 1970. Well, the final step was done in 1970. So this is the answer to the E problem, and also so Hilbert's 10th problem is also undecidable. And the last step in this proof was done by a very clever Russian. That people had got they got an argument most of the way, but there was a very tricky step remaining to be done. And this Russian guy called Matiezevich, who we will on the whiteboard abbreviate to M dot, he solved it. So Yuri Matiezevich, he solved it in 1970. Right, it's before we break, just to say, actually, there's an interesting connection between these two problems. There's a mathematical connection in that if somebody had found an algorithm that would decide whether a sentence in first order logic is valid, then using that algorithm, it would have been possible. So from that, we would be able to derive an algorithm that would find out whether a Diophantine equation has an integer solution. So a positive answer, had there been one, to the E problem, the Entscheidungsproblem, would have given a fortiori a positive answer to the Hilbert's 10th problem. But of course, for negative answers, the implication works in the other direction. So when there was a negative answer for this problem, that didn't give us any information about Hilbert's 10th problem. So in the end, the negative answer was found to Hilbert's 10th problem, and then one gets from that also the Entscheidungsproblem is undecidable, but we already knew that. Okay, so it's time for a break now. So let's, I'll pause the recording. Let's have a break. If you've got any questions, feel free to ask. So a break till 1:15. 5 o'clock on that table. Small. Okay. Good. Okay, so the important thing, as somebody mentioned, that a lot of you in the room will not know technically what the meaning of Hilbert's Entscheidungsproblem is, because what does it mean to say a sentence is logically valid? And I'm sorry, I cannot tell you that in this course because it's the topic of another course, which will actually be next semester, of mathematical logic. So for the sake of this course, you just have to accept this as a natural mathematical problem that was historically the problem that led to the very first undecidability result. So the very first result that it is impossible to find an algorithm to solve a particular problem. And the very idea of this impossibility result led to a whole host of new developments. Because up to this point, people had been looking for algorithms to solve problems, and the idea was you recognize an algorithm when you see one. You can see if you've got a list of steps to follow, you can see whether that's a precise description of the steps you need to follow to solve a problem. So you can recognize an algorithm when you see one. If you want to prove that there does not exist an algorithm for something, then you need to have a precise delineation, that's a precise scoping around the notion of algorithm itself. You need to know, you need a mathematical definition of what an algorithm is in order to say, well, this is what an algorithm is, and there is no such thing that solves my problem. And this did not exist at all until the 1930s. And at the time, computers did not exist, so people didn't even have the idea, well, an algorithm is something I can program on the computer or something like that, because computers didn't exist. So the Church, Alonzo Church and Alan Turing solved this problem in different ways. Church came up with his notion of algorithm. That's something called the lambda calculus, which is a core feature of functional programming languages. That will be one of the models of computation that can be researched and presented in the homework part of the course. Alan Turing came up with his notion of algorithm, which was the notion of Turing machine. And that's the notion we're going to start with, use on the course. So what I want to end today with, we've got 2 more hours of lecture. I want to introduce you to the notion of Turing machine. Probably some of you, well, I know that some of you have met it before. There's just for this lecture on the course, for those of you who took computational complexity last year, there was an overlap with the computational complexity course. So we're going to understand the notion of Turing machine, which was Turing's answer to the question, what is a good general mathematical definition of the notion of algorithm? So when we get to the technical side, we'll go through it at a reasonable pace. But before getting to the technical definitions, I'd like you to just try. I mean, we've all got experience with programming computers and things like that now, but just try to think about what life would have been like before you knew about computers and before you knew about programming. And your notion of algorithm was like a set of instructions, like Euclid's algorithm or something like that, that you can follow on paper. And if you were trying to give a mathematical definition that precisely defines what the scope of the notion of algorithm in that sense is, it's not at all obvious how to do it. So Turing he came up with his definition, and he wrote a beautiful paper on it called something like On Computable Numbers with an Application to the Entscheidungsproblem. Even though this was written in the 1930s, it's still very readable today, and I'm going to put a link to the paper on the course webpage. So I recommend you have a look at that. But Turing, what Turing did, I mean, Alonzo Church just came up with the lambda calculus and said, an algorithm is something we can write in the lambda calculus. So there's no further justification than that. So it sort of looked totally preposterous to most people at the time. Whereas Alan Turing actually made a reasoned and very well presented argument justifying his notion of algorithm, his notion of Turing machine. And he based it on the following general desiderata. So in general, I'm not going to be very philosophical on this course, but it is really worth, I think, trying to appreciate where the notion of Turing machine came from at the time that it came up. So we're just going to make an exception now and try to try to understand Turing's thought process as we can, as far as we can. So Turing's desiderata, things one would like, as the plural, desideratum is the singular, desiderata for a mathematical notion of algorithm. Or let's say even a mathematical definition of algorithm. So things the definition should fill are fulfill are an algorithm is supposed to be some process that we follow to compete with. So it should be a description of that process that we follow, but moreover, to be able to communicate it to someone else, it needs to be fine. So an algorithm should be, I'm just going to sometimes abbreviate words, like, so this is should, S-H-L-D, should be a finite description. This is the kind of writing one does in SMS messages. So finite description of a process of computation. Finite here is very important. shouldn't be, of course, it should not be, of course, a partial description, but if it's an algorithm that we can follow step by step, it should contain all the information that's necessary to follow it. So it should specify, it should again specify the computation process in its entirety. Computation. So there should be nothing left out. You shouldn't have to rely on having some eureka steps when you suddenly have some inspiration following an algorithm. It should tell you what to do. And related to that, so in fact, you shouldn't rely on any creative input. So the algorithm should, so this is, it should specify it all the way through. And in addition to that, it should give instructions for every little bit. There should not be anything left unsaid in the algorithm. So, the process of following an algorithm should be able to be carried out without any creative input. So this is, the algorithm should specify anything. We shouldn't need to put in anything that's not explicitly said in the algorithm. So this was Turing's thought process. He got to here and he said, in consequence of all this, the process of following the algorithm should be one that can be carried out by a machine. So therefore, the process of computation should be able to be carried out by a machine. Now, how is the machine going to work? Well, the machine is going to be some sort of physical device that's going to do its computing. Computing is going to be following the algorithm, so it's going to be taking time. At the same time, if we're a human following the steps of an algorithm as we go along, we need to do some calculations, typically some manipulations on the way in order to see where the algorithm is taking us. So we need some working space. So the machine is going to be similar. It's going to perform its operations in time, step by step, and in space, using some working space as and when necessary in order to perform calculations. So the machine, I don't know if you know this symbol. I mean, this is 3 dots in a triangle here. This in English mathematics, this means therefore. I don't know if that's I don't know if it's an international symbol. So this 3 dots. So the machine. So the machine will perform steps in time, and use working space for its computation, for its calculations, let's say. And if an algorithmic process comes to the conclusion, if it finishes, then obviously the machine must, well, if it finishes, it will finish in finite time after a finite number of steps. And when it finishes, only a finite amount of space will have been used by the machine, because you can't use an infinite amount of space in a finite time. But on the other hand, for the notion of algorithm, it makes sense to consider a notion that we do not bound the time and space in advance. We have a sequence of steps and we'll carry them out for as long as we need to, and using as much calculational space as we need to. It's going to be hard to always know how to bound that in advance, but we're going to always keep our fingers crossed and hope that eventually, after not too much time, we'll terminate with an answer. But we should not artificially bound time and space in advance. Of course, in the real world, time and space is bounded in advance. Although we now have much more space on computers for computing power than we did, say, 30 years ago. I mean, not an enormous amount of space, but still there is a limitation. There are limitations to time and space. But for the theoretical notion of algorithm, it's natural not to bound time and space in advance. And notice actually that's when we're going for negative results, such as there does not exist an algorithm to solve a problem. We want the notion of algorithm to be as generous as possible, to be as broad as possible, because then the negative result becomes stronger. It's actually better that we don't, even if we don't bound time and space in advance, we're still unable to get an algorithm to solve these problems. Okay? So Turing's definition of a Turing machine indeed meets these criteria. And when you think in this way, one's kind of naturally led to something like a Turing machine. I mean, one could think of many different kinds of machines that would fit these criteria. But another thing that one wants to do if one's getting a mathematical model is try to make the mathematical model as simple as possible. So that we don't have unnecessary complications in dealing with the model. Try to make the model okay. So out of interest, how many people have been to a course in the past in which you've seen or read a book in which you've seen the notion of Turing machine, including a precise mathematical definition of Turing machines? I wonder if it's 100% of the people in the room. Okay, not 100%, but the majority of people in the room. So I'm sorry for people that have seen Turing machines before, but anyway, one can always, I mean, what I like to do when I see that, or at least think about the definition of the Turing machine for the umpteenth time in my life. So umpteenth is a word we use in English to mean some large number of times. It's always nice to think about what's a great contribution Turing made in coming up with this really lovely notion. So, I mean, I think it's a really beautiful mathematical definition. It's now getting on towards, well, it was from 1936, so it's in its 80s now. It's maturing, but it's maturing very well. It's still a very important definite mathematical notion. Even though computers have been developed since then, for doing the mathematics of computation, Turing machines are still, I think, the most widely appreciated model. So the Turing machine, there are different definitions, and the one we're going to use is not exactly the version in Turing's paper, but it's all the different definitions are equivalent, and I'm going to talk about that to some extent. As you may know, Turing machine is a machine that computes with performing its calculations on paper, and the paper is a tape, which is infinite. Well, I think in Turing's original article, it was infinite only in one direction, but I think it's convenient in a lot of definitions. Not to deal with it this way, it's convenient to have it infinite in two directions. So you may say, well, infinite paper tapes don't exist. Well, indeed they don't. But the point is, we're not bounding the amount of space in advance. It doesn't actually need to be an infinite tape. The point is, we can just call on more tape any time we need a bit more space. We can ask for a bit more tape to be sellotaped, if you like, to the end of the current tape we're working with. So we might as well think of working with an infinite tape. And the tape is divided into squares. So here are the squares of cells. And in the cells, you can, so the cells are either blank if you haven't used the tape. So most of the cells on the infinite tape, you can consider, say, this has been a 0 cell and numbering them if you wanted to number them into the negative integers this way, the positive integers this way. But in the cells, you can write symbols from a finite alphabet of symbols that we're allowed to write. So we're going to have a tape alphabet, gamma, that's the tape alphabet, that's capital gamma, and it's going to consist of the symbols we can write on the tape. So in this case, I'm just going to have binary words on the tape, so 0 and 1. And we also we always assume that the tape alphabet contains what I write as a square like this, which is blank. This is a blank cell. So when you start the computation, all except finitely many, these squares go all the way along the tape, but all except finitely many cells of the tape are blank. And you may have some input that's given on your tape, which consists of the non-blank symbols. So for example, in the case of this machine, we're going to start with the input 0, 1, 0, 1, 1. We've got 5 symbols, 5 binary digits as input. This is a blank square, this is a blank square, and my convention is all the squares to the left of here and all the squares to the right of here are blank. So this is the non-blank portion of the tape. And the machine looks at its tape and it moves its head, using what's called the head of the machine, which is the machine is currently looking at the symbol 0 at this square. When it looks at a square, it can see what is on the square, and it can, if necessary, replace it with another symbol, and it can move left or right. And actually what it does is determined by 2 things. It's determined by the state that it's in, so the machine always has a current state. And my convention is that it's always going to start in a special state called start. When it's in a special state called, when it's in a given state with the head in a certain position, what it does is it looks at the current symbol on the tape, where the head is. It looks at its instructions. The instructions are given in what's called the transition function. And if one of the instructions applies, it applies the instruction and does what it's told. And the instructions, this transition function, is going to be a finite amount of, it's going to be a finite number of instructions for what to do in finitely many different situations. So in this case, there's going to be an instruction that tells us what we look for in our table of instructions, which I'm going to write down as we go along. We look for what to do in the start state when the tape head sees the symbol 0. And to find out what to do, we look in our instruction table, and it tells us that if we're in the start state and the tape head sees the symbol 0, then we stay in the start state, even though we're not starting, but we still stay in the. We're going to have a number of states, but we're going to keep in what's called the start state. We're going to keep 0 on the tape And then there's a third piece of information we give here, which is a displacement to move the head. And you can either move it, the usual notion of Turing machine is you can either keep it where it is, or you can move it 1 square left or 1 square to the right. So I'm going to do this displacement by having a 0, a +1, or a -1 here. And of course, I can just write 1, but I'm going to put the pluses and minuses to distinguish from the alphabet here. In this case, we stay in start, we go to 0, we keep 0 on the tape. If I put a 1 here, we would replace what's on the tape with 1, and we move the head 1 to the right. So let's actually make that transition, as it's called, from the current configuration of the machine, let's put the head back. This is the starting configuration of the machine. We're given our input, we're at the left edge of the input, we're at the left square of the input, and we're in the start state. That's the starting configuration. Now we move 1 transition, and it says keep the 0 on the tape and move 1 to the right. So now we need to know, we're now still in the start state, we need to know what to do. We see a 1, which we don't have the instruction for that yet. There might not be 1 in the table, in which case we just don't do anything. And in fact, there is going to be 1 in the table with an instruction here. And the instruction for this machine says, if we see 1 on the tape, and we're in the start position, then again, we keep 1 on the tape, but we go to a different state now, which is called the odd state. And again, we move the head 1 to the right. Okay, so we're in the start state, we see a 1, we keep the 1 on the tape, that's this. We move to the odd state, and we move the tape head to the right. And now in the odd state, and we see a 0. So we need an instruction for that. I'm just wondering where to put it. That's why I was moving around. So in the odd state, and we see a 0, then we stay in the odd state. We keep the 0 on the tape, and we move 1 to the right. So we stay in the odd state, we keep the 0 on the tape, and we move 1 to the right. We're now in the odd state, and we see a 1, and again, we need an instruction for that. We don't have an instruction for that yet. So in the odd state, we see a 1. In this case, we go to the start state, go back to the start state, we keep the 1 on the tape, we move 1 to the right. Go back to the start state. Keep the 1 on the tape, and we move the head to the right. We're now in the start state, we see a 1. So again, the start state, see a 1. We move to the odd state, we keep the 1, and we move the head 1 to the right. The odd state, keep the 1, and we move the head 1 to the right. So we're now in the odd state, we look at the tape, and we don't see anything. We see the blank symbol. We don't have yet an instruction for what to do for the odd state and the blank symbol. So for the odd state and the blank symbol, let's put it here. If we're in the odd state, we see the blank symbol, then we'll go to the accept state. We'll keep the blank symbol, and we won't move the head at all. So let me call that +0. We don't move the head at all. And just as a matter of interest, if we were in the odd state and we saw if we were in the start state and we saw a blank symbol, then we move to a special state called reject. We keep the blank symbol, we also keep the head where it is. And this specifies a very simple Turing machine, that if you give it a word, a binary word, a word of binary bits, so a sequence of binary bits, and you start with the head at the left in the start position, that's your starting configuration, it will always move its head from left to right until you get to the first blank, alternating according to these rules between the start state and odd state until it gets to the end. We'll always, by the way we've written the rules, it will always leave the input word unchanged, although if we did use different words, if we'd used different rules, it could have overwritten the input word with new information, but we didn't do that. And when we get to the first blank square, it will either go to the reject state or the accept state. And we're not going to have any instructions for things to do from the accept state on the reject state, because these are what are called halting states. You don't have any transitions out of them. So we will either halt in accept or reject. The idea is we give it a word of zeros and ones, and this computation is going to accept some of those words by eventually scanning the word, going into the accept state, and is going to reject some other of the words by scanning the word and going into the reject state. So can anybody see in the end, what this computes? So which binary words of zeros and ones will be accepted and which will be rejected? So can anyone see that from the rules? So this one was accepted in the end. Oh, I didn't do the last move. So from odd in the blank word, we move to the accept state. We keep the, sorry, not the blank word, the blank square. We kept the blank and we don't move ahead. So we accepted that word. Does anyone know what it's computing? Otherwise, yes?
It's looking whether there is an odd or an even number of ones in the string.
Exactly. Yes, very good. So the way it's done, it will be in the odd state, exactly at those squares to which there has been an odd number of ones to the left of the current position. By the time you get to the end, it will be in the odd state if there's an odd number of ones in the word, and then it goes to accept only if it's in the odd state. So it will accept exactly those words that have an odd number of ones in them and reject those words that have an even number of ones in them. Okay, very good. Very, very simple computational process. Turing machines can get a lot more complicated than this. In the exercise class today, we'll be programming some more complicated Turing machines to get the feel for it. I don't want to spend too much of the lecture going through examples of complicated Turing machines. But let's just have a look at mathematically what we needed to specify this Turing machine. So the Turing machine is given by specifying the tape alphabet. Let's get over to this board. So fundamentally, a Turing machine is given by a mathematical, you think of it as a physical machine, but it's given by a mathematical definition. A certain amount of finite information describes a machine, and you think of that machine as an algorithm. So in this case, it is a very simple algorithm that looks at a word and sees whether it has an even number or an odd number of ones in it. Okay, by word, I mean a finite sequence of zeros and ones in this case. So to specify a Turing machine, and I need to move the camera. I should have moved the camera a while ago. So now I don't need to move it. Oh dear. Well, this thing happens all the time. So last year in one of my courses, there was a very helpful student who was always aware of whether the camera was pointing in the wrong direction somehow. So if one of you manages to have that sort of awareness, that would be fantastic. Despite a lot of trying, I seem to not be able to develop it myself. Anyway, to specify a Turing machine, we give a finite tape alphabet. So the tape alphabet always has the blank symbol because you always require all but finitely many squares of the tape to be blank. But you're allowed to have any other finite set of symbols for your alphabet. So you don't need to restrict to binary words. So we give a finite tape alphabet, traditionally called gamma, capital Gamma, which always contains the Planck square. We give a finite number of states that the machine can be in. So in this case, the states is start, odd, accept, and reject. And the state, often one uses the set Q, sorry, the symbol Q for the set of states. It's traditional in computer science. So you can hear that the states is start, odd, accept, reject. Finite set Q states, which always contains the start state. You might think you might always want to accept and reject, but we're not going to insist that those are always there. So one of the nice things about Turing machines is that they're a little bit flexible in what you can do with them. So one of the jobs you can do with the Turing machine is this job of looking at strings of symbols and deciding whether to accept or reject them. This is called language recognition. I'll define that more formally in a moment. But another thing you can do is start with symbols and look at how the Turing machine transforms the symbols on the tape. And that's computing a function from the input string to the output string. That's another very important mode of computation. And if we're looking at language recognition, then we will want to have accept and reject states. But if we're just looking at how we transform the symbols on the tape, then it doesn't make sense to accept and reject the input. We're rather looking at how we transform the symbols on the tape. So we're not going to require having accept and reject in our set of states. So the third piece of information is what's given in this table of instructions, which is called the transition function. So a transition function this is called delta. It's a very poor delta, so I'll write it again. This is called delta, and this is a function that, so it looks to see, so as its input, it takes a pair of the state you're in together with the tape symbol you're reading. So the domain of the function is states, so pairs consisting of states and tape symbols. And the codomain of the function is, so then it gives us the instruction which state to move to, what symbol to overwrite the current symbol with, and which direction to move. So it's a function, and the codomain is a triple consisting of a state, another tape symbol, and a displacement, either -1, 0, or +1. And here you notice I've written a funny arrow. This is just a bit of being pedantic, unnecessarily precise, perhaps, on my side. So what this means, by this I mean a partial function. At the start of the notes, there's a page or two of mathematical conventions I'm going to use in the course. But what a partial function is, it's a function defined on a subset of the domain. So we don't need to specify an instruction for every single state and symbol combination. Okay? It only needs, we need to define the function on some set of pairs consisting of state and symbols. So this just means a partial function, so a function defined on some subset of the domain. Okay, and you can look at the notes for more clarification about that if you wish to. So this is a partial function because here we've got three things. We've got three symbols and four states. And if the function is defined on everything in its domain, there will be 12 instructions, but actually we've only got 6 instructions what to do here. And we specifically do not want any instructions to be, we do not want any transitions coming from the halting states accept and reject. So then typically we execute So execute has 2 meanings in English. One is to carry out a computation, like izvajamo, I get izvedemo or izvajamo, I don't know, something like that anyway. You can tell me what they're, anyway. And the other word is much more, the other meaning is much more grisly. So here, anyway. Anyway, we carry out a computation, a Turing machine, by starting it off in the starting configuration of the state. Start is start, and the head position is the left symbol of the input string, input word. I'm thinking if the non-blank symbol is being a word somewhere on the tape, and the tape head will be at the left symbol of that. We're allowed to have an empty input word, and if the input word is empty, well, it doesn't actually matter where the head symbol is. So that's a special case. But nonetheless, the typical case is you're in this, we start in the start state, and your head is at the left symbol, pointing at the left symbol of the word on the tape. And then the instructions are followed until, well, let's say, it's better to put the either here, I think. So either, there are 2 possibilities, until a halting configuration is reached. So let's call this a starting configuration is reached. And the idea is when you compute, you start off in the starting configuration, and your instructions tell you how to go from configuration to configuration. And a configuration of the machine is exactly what we drew on the board. So the configuration of the machine is the contents of the tape, together with the tape head position, together with the current state. That's a configuration of the machine. Every step of computation takes you from the current configuration to the next configuration. And we either get to a halting configuration in which there is no further step of computation possible. There's no instruction that applies to it. So the instructions are followed either until we reach a halting configuration, or if we don't reach a halting configuration, instructions are followed forever. So the Turing machine runs forever. It goes, if you like, into an infinite loop. And it need not be a loop in that it need not ever reach exactly the same configuration. Again, it may shoot off to the right along the tape and never stop, for example. So it may not exactly get into a loop, but it does not do us the courtesy of halting. So a halting configuration is reached, or the machine computes forever. It does not halt in this case. And as probably almost everyone in the room will have heard, there's a very famous problem called the halting problem, which is going to be something we look at in the next lecture. The halting problem is the question, can we tell, given a machine, whether and an input, whether we're going to reach a halting configuration or not? And as you, I mean, I think it's no secret, it's part of almost mathematical popular knowledge. That is a very basic question that is not decidable. That's going to be one of our first examples of an undecidable question, this halting problem. Okay, so just two things to say before the break. So just to underline configuration, the idea of a configuration is important. We have the starting configuration. We go from configuration to configuration. So configuration equals the state of the machine together with head position, the tape content together with the head position. And in the notes, there's a rather formal definition, a mathematically precise definition of what the state of the machine is and how to define this computational process in a precise mathematical way. So I suggest you think about that for yourselves. How would you define that? And then look at the notes. From the point of view of the lecture, I think what's important is to understand how the machines compute, to understand the information we need to define a machine, and and to understand what we can do with Turing machines. And the last of those is what we're going to address in the third hour of the lecture. So it's 4 o'clock now, so we're going to have a break until 4:15, and we'll resume. Right. So we've got the notion of a Turing machine. This is, the camera is now pointing at this board, so it will at least appear on the recording. I'm going to remove it. We've got the notion of Turing machine, and we've seen one very simple example of a Turing machine. And what that Turing machine did was it looked at a word over an alphabet, and it either accepted the word or rejected the word. And for the particular Turing machine we looked at, it accepted the word if it contained an odd number of ones, and it rejected the word if it contained an even number of ones. And this particular Turing machine was illustrative of a very general type of Turing machine, which is using a Turing machine to recognize a language, as they're called. So in mathematically speaking, a language, you give yourself some alphabet. In our case, the alphabet was 0 and 1. So we're looking at words consisting of zeros and ones. And in mathematical simplification of the common idea of the concept, a language is simply a set of words. So the Turing machine we were looking at was recognizing the language of those words that contain an even number, or sorry, not an even number, an odd number of ones. This is one of the things we can do with Turing machines. In the notes, I call this the modus operandi of Turing machines. So operandi here is plural, is the ways of using Turing machines. And the first way of using a Turing machine is Turing machines. So Turing machines, I'm going to abbreviate TMs as language recognizers. Recognize languages. So just to remind you, or tell you if you haven't seen this before, the notion of a language, which I've just gone over. So given an alphabet, typically one uses a capital Greek letter sigma for an alphabet. So So this is a finite set. You think of them as symbols. So in the case of our Turing machines, our finite, the finite set, the alphabet from which we were forming the words was just the alphabet of 0 and consisting of two symbols, 0 and 1, the alphabet of binary bits, binary digits, sorry, bits, binary digits. Bit itself is an abbreviation for binary digit, so you don't need to say binary bit. But given an alphabet, sigma, a finite set, a language, in the mathematical sense over sigma, is given by, it's just a subset, L. This particular language is the language L, which is some subset of the set of all words over sigma. So sigma star, I don't know if you've seen this notation in other courses, it's very common computer science notation. This is, again, you can look at the start of the LaTeX notes when they're available online, which will be later today, for the notations used in the course. But this is the set of words over the alphabet sigma. And the word is simply a finite sequence of elements from sigma. So like the sigma is the two-element set of 0 and 1, the alphabet of bits. A word would be 0, 1, 0, or 0, 1, 0, 1. These are all words over sigma, and L is just a set of such words. Something to pay a little bit of attention to is sigma star, the set of finite sequences, or the set of words, which includes the empty sequence. So we have an empty word. So including the empty word. And computer science, at least, one often uses this sort of curly little epsilon for the empty word. It's not the only symbol for it, but it's a standard notation. And the language is just a set of words. So another thing to be careful about is one has the empty language, which is the empty set. One also has the language that contains exactly one word, and that word is the empty word, which is different because that language has one word, but it's the empty word. We also have another trivial language, which is like the whole of the language of all words, so to speak. I mean, trivial in the sense it's not very computationally interesting. And in the case we were looking at, we were looking at the language of those words that contain an odd number of ones. So that particular language would not contain the empty word, because the empty word has 0 ones in it, and 0 is an even number. Anyway, a language is a subset L of sigma star, and we're going to look at how a Turing machine recognizes a language. So, a Turing machine will be viewed as recognizing some language over sigma. So namely, it recognizes a subset of sigma star, the set of words, if, so for a Turing machine to count as a language recognizer, I'm going to ask for it as well, let's just write it briefly in symbols. So we have accept and reject states. So it has particular accept and reject states, as we did. And these two states are halting states. Meaning, I didn't define it mathematically. It's not worth spending time on the definition. It's in the notes, but the idea is very simple. A halting state is a state for which there are no possible transitions out from that state. Okay, so you can never, you get into that state, the Turing machine can never get out of the state. it holds. And secondly, we require that obviously the input alphabet needs to be a subset of the take alphabet. And we don't want to confuse the input alphabet with the blank symbol. So we require that we're not going to allow the blank symbol to appear in our input alphabet. So it's a subset of the take alphabet with the blank symbol removed from it. So that's the way of saying that. I think those are the only requirements. Let me just, yeah. So given this, given such a Turing machine, the language, let's call it M, the Turing machine, the language recognized by M let's underline it, because we're defining this concept. The language recognized by M is, I'm sorry, it's right at the bottom of the board, but I'm going to squeeze it in anyway. Hopefully everyone can, maybe I can put it here actually. So write it as curly L. Let me try and write it a nicer curly L. Curly L of M, language recognized by M. So this is the set of all words over sigma. So that's all W belonging to sigma star, such that if the TM, the Turing machine M, is run on input word W, it holds in the accept state. Okay, so to recognize a language, you require, the definition is, well, any Turing machine that has these two halting states and which contains the input-output alphabet, sigma as part of its take alphabet, you can define the language recognized by the Turing machine. There's something a bit curious about this definition. I don't know if anyone has seen what it is. There's something we're not using. Yeah, so we haven't actually used the reject state in this definition. Well, this is the standard definition of the language recognized by M. But the reason we haven't used the reject state is because there are going to be two different strengths according to which a Turing machine can recognize a language. This is the weakest. This is the weakest requirement for it to recognize a language. But we're also going to have a stronger version in which it recognizes a language in a stronger way. So let's do that on the other board. So the idea here, so far, is the Turing machine, the language it recognizes, simply those input words that it ultimately accepts. We give it other words, it may reject them. On the other hand, it may terminate in some completely different terminating state, or it doesn't. This definition doesn't say anything about what the Turing machine M does on input words that are not in the recognized language. So it may possibly terminate in the rejecting state, it may terminate in a different terminating state, just not the accepting state, or it may compute forever. Those are the three possibilities of what might happen with a word not in the language. So we're going to have two strengths of recognizing a language. Thank you very much. So we say that Turing machine M semi-decides L, so L is a language, if L equals the language of the Turing machine. So in other words, it semi-decides a language if that Turing machine will accept every input word that's from the language, and given any word that's not from the language, it will not accept it. And not accepting it means it may go to a reject state, it may go to some other terminating state, or it may compute forever. So just all that's required is it accepts a word if and only if that word belongs to the language. The stronger version is that the Turing machine decides L if it decides it, so it indeed accepts only those words in the language, and furthermore, for every word over the alphabet, so it is a word over sigma. So this is the set difference operation here. So I'm taking away the set of words, the language from. So this is simply saying for every word over sigma that's not in the language, I use the same words that I used here. If M, and for every word not in the language, if M is run on input word W, it terminates in the reject state. Okay, so for this stronger notion of deciding a language, we have that whatever input word we give to the Turing machine, it is guaranteed to terminate, and moreover, it is guaranteed to terminate in one of the two states, accept or reject. It will terminate in accept if and only if the input word belonged to the language, and terminate in reject if and only if the input word did not belong to the language. So the difference between these two concepts is if a Turing machine decides a language, we get the information, we give it an input word, we'll get the information, yes, the word belongs to the language if it terminates in accept, and we'll get the information, no, the word does not belong to the language if the machine terminates in reject. And it's guaranteed to do one of those two things. So we're going to find out, as long as we're patient enough, we will be able to find out an answer to the question, does the word belong in the language? The Turing machine only semi-decides the language, then we're guaranteed to, if we give it a word in the language, we're guaranteed to eventually be told that our word belongs to the language. We're going to find out that positive information. But if we give it a word that's not in the language, there's no guarantees at all over behavior. And the Turing machine could just compute forever and we'll never get an answer back. So we may not be able to tell if a word does not belong to the language. So clearly, if a Turing machine decides a language, then it semi-decides the language. That's trivial, it's a stronger definition. The converse is, well, this really is a stronger definition in the sense that one of the first core results of computability theory is going to be to find a language that we can semi-decide, but it's not possible to decide the language. Okay, that's going to be the major goal of next week, or one of the main results of next week's lecture. And just to complete these definitions here, the idea of the problems that we had at the start of the lecture, all of these can be couched. So there's Hilbert's 10th problem and Hilbert's Entscheidungsproblem. Both those problems can be formulated in terms of is a certain language decidable? So in the case of Hilbert's 10th problem, you have a language such that the well-formed words in the language represent Diophantine equations. And then we want to ask for an algorithm that solves that. So we're trying to ask, does there exist a Turing machine that decides that language? That's ideally what we would like to do. In fact, in that case, it's not difficult to see there does exist a Turing machine that semi-decides the language. If a Diophantine equation has integer solutions, you can search for the integer solutions, and eventually, if a solution exists, you'll eventually find it. There are only countably many possible tuples of integers that could form the solution. Anyway, so these questions are, this is essentially a mathematical framework which we can address the solvability of Diophantine equations and the Entscheidungsproblem. And to have the terminology that I already used informally earlier, now we can define it formally. So a language L is semi-decidable, if there exists a Turing machine M that decides it, but semi-decides it, and the language L is unsurprisingly decidable if there exists a Turing machine and perhaps decides it. Okay, these are important concepts, so it's worth spending some time to think about this. If you've not been able to follow it at the speed of the lecture, also have a look at the lecture notes, and these are really, really important concepts to get your head around. Okay. Any questions on that while I'm clearing the board? And I will remember to move the camera when I've cleared the board.
Is there a difference between terminating and halting?
Oh, sorry, yes, it's a good question. I'm using terminating and halting as synonyms. So that's two words that have the same meaning. Just to avoid, just to not always say the same word.
So a language can be semi-decidable and decidable at the same time.
Well, any language that's decidable is semi-decidable, according to these definitions. Although quite often in formal usage, one would say semi-decidable to mean only semi-decidable. And maybe I should say that semi-decidable is also called semi-computable and computably enumerable and recursively enumerable. So there's a list of these synonyms in the lecture notes. I'm not going to write them all on the board. And decidable is also called recursive and also called computable. So there are different, and we'll move to other terminology later in the course, but for the moment, this is the nice, I like these words because they're really informative about the concept. I mean, they really reflect the concept, semi-decidable and decidable. Okay, so that's one use to which we can put Turing machines. Just very briefly, I want to consider another usage. So this is Turing machines as computing, or let's say for Turing machines for computing partial functions. I'm again going to consider Turing machines as we've defined them. And now the idea, and I again want to give it an input string. But now, rather than looking at do we get into an accept state or a reject state, I'm going to look at do we terminate? And if we do terminate, what is the current word on the string when we terminate? Sorry, not on the string, the current word on the tape when we terminate. So to do this, given a TM, we'll assume given a Turing machine that satisfies again sigma. We're going to again have an input alphabet and an output alphabet. We'll call sigma the input alphabet. Sigma is again So the alphabet, we want to transform words over the alphabet sigma to other words over the alphabet sigma. We're going to again assume that's a subset of our take alphabet that does not contain the blank symbol. And we now want to compute until the machine halts. We could just halt in any state, but I find it quite useful to have a particular state that we want the machine to halt in. So I'm just going to call that state, I think in my notes I call it halt, but maybe I should just check that. Yeah. Oh, thank you very much. So I said I was not going to forget to move the. Right. So we have not just that the machine halts, but it requires in a particular state that we use to signal that it's halted in the way we want it to halt. So halt, we have a distinguished state which we call halt in the set of states. And we say that, let's call this Turing machine M. We say that M computes a partial function f from a set of words over sigma to itself. So again, I'm using the partial function symbol here. The idea is that this is a function that's defined on some set of words over set of words over the alphabet sigma, namely the domain of the function. So it's a function from some subset of sigma star, and for any word in that subset, it will give us back another word, namely the word that the input word gets transformed to by the function. So M computes a partial function f if the following two conditions are for any word w in the domain of the function f. This means words on which the function is defined. So where's the green pen? Defined. For any words in the domain of f, if run on input word w, the Turing machine halts with only f of w on its output tape, so not its output tape, on its tape, and with the tape head, Turing machine head, at the left symbol of W. So we're requiring a Turing machine to compute a function. It's going to transform the input word into the word f of w, so into the correct word that's wanted by applying the function to w. And moreover, it's going to transform that, leaving only that word on the tape and resetting its head position to go all the way to the left. You could imagine relaxing some of these restrictions, so you might not really care where the head position is of the tape. It actually does not change the strength of the definition. But it's nice to require the machine to reset the hex symbol to the left of the tape, because that then makes it easy to compose these functions, to apply one function after another, because the Turing machine will leave itself in a state that's appropriate for running another Turing machine on it, with the head position at the left. So that's the first requirement, which is what the Turing holds in the state hold. And again, hold here should be a halting state. And the second requirement, so this is what it needs to do on a word that's in the domain of F. And the requirement is, if you give it a word not in F, and not in the domain of F, so for any W not in the domain of F, if run on W, on input W, the TM does not halt in the hold state. It can halt in another state, but does not halt in the hold state. So the hold state is indicating, yes, I have found a word that's in the input of the function, and I have successfully computed its image according to the function. So it does not halt in the hold state. Here we're computing partial functions given an input word, give me back an output word. You can imagine these things are very useful. For example, if we want to compute a function on numbers, you can encode numbers as a binary string in binary, and you can run a Turing machine that will take the input word on the binary string and return another binary word on the output on the tape. Sorry, take the input word as a binary string on the tape and return another output word on the tape, and you want that to be a binary representation of the results of the function. Yes, there's a question.
On the first point, you said that we move to the left of the symbol W, but shouldn't be there unless W, because after we finish, there's second W on the.
Yes, thank you. Very good. It should be F and W on the tape. And then, so it's pointing at the leftmost symbol of the word F and W. Thank you very much. Okay. So hopefully you can see the use of such computing partial functions, and I think that's enough. So for the moment, that's two modus operandi of Turing machines: accepting languages, so recognizing languages, either semi-deciding or deciding them, and computing partial functions. Okay, one thing I just want to end very briefly by discussing somehow the generality of the Turing machine model. So it's very nice in that it's quite concrete and at the same time quite simple, and one can do things with it, but it looks a little bit arbitrary. So how arbitrary is it really? So, you know, you get almost every part of the definition. You could imagine making the definition in a slightly different way, and maybe you'd get some other completely different notion of computation if you did. So there are many variant notions in Turing machine. In case you think it's a bit arbitrary what we're doing. So one such thing as tape is only one-way infinite, so infinite to the right, say, rather than two-way infinite. That's making a more restrictive model. Another one is what makes an apparently more general model would be to allow, instead of having the Turing machine with only one tape, have the Turing machine with many tapes. So allow many tapes, each with its own head. Another possibility is not just to have one head per tape, but several heads per tape. You could imagine that might give you even more power. So allow several tapes, sorry, heads per tape. I'm not going to write them all down. Another possibility would be to have several tapes and some number of heads, and you allow the heads to move between tapes as well as within the same tape, or something even more general, perhaps within that sort of direction, is instead of having one-dimensional tapes, have, say, two-dimensional tapes like sheets of paper, or even 3 dimensions, or even multi-dimensional tapes. So allow multi-dimensional tapes. Different direction is, instead of just having one symbol per square, allow these squares to then contain arbitrary words of arbitrary length. So allow tape cells to contain words, not characters. I think there might be some others mentioned in the lecture notes, but I mean, you know, one is limited by one's imagination here, so only by one's imagination. There, you can imagine lots of variations along this line. So let's say etc. And the amazing thing is, lots of these have been explored in detail, and all variations of this kind of form, or similar, or even not so similar, all of them turn out to be of the same power as the one-tape Turing machines that we've introduced. So all such models turn out to be equivalent. What equivalent means is that take some such model like this, so say a model with a 2-dimensional tape. It turns out you can simulate any such Turing machine on a one-tape Turing machine. And in the other direction, which is much easier, you can simulate any one-tape Turing machine on a multi-dimensional tape machine. But in any case, each one can be simulated with the other, and they compute the same things. So we're going to see a little bit of that sort of equivalence next week, and then we'll go to the main point next week, which will then be the point of exploring this sort of thing is to reassure ourselves that the arbitrary choices we have made, the seemingly arbitrary choices we have made in the definition of Turing machine, are actually not affecting the notion, the fundamental notions of computability and decidability and semi-decidability. Okay, still got a few minutes, so I just realized I did forget to give a very important definition here. So let me just do that. So we end with a technical thing, and then you'll have a little bit of a break before the exercise class. Oops. So the thing I forgot to add here is we've got the notion of a Turing machine computing a partial function. So then one can turn that to, if we've got a particular Turing machine, we can say, does it compute a partial function? It needs to obey these quite tight rules in order to do so. And if so, which partial function does it compute? We can turn that around, and given a partial function, we can ask, is it possible to compute it? Does there exist a Turing machine that can compute it? So the important definition I forgot is we say a partial function f from a set of words x sigma, the set of words x sigma is computable if there exists a Turing machine. A Turing machine that computes. Okay. That is the end of today's lecture. One final thing about the exercise class, I don't know if you saw on the webpage, but today and next week it's in in the computer lab in room 310 rather than in the standard timetable room. So today exercise class room 310, 3%. Okay, good. I shall stop the recording. Are there any questions?